Almost like a service that the juggler provides, like changing.
Okay,
By learning the speed.
so let's chit chat about this assignment, okay? And there seems to see some raucous debate about some of these answers. So on 36, both of them should have 8 waters if you do that right. One will be spontaneous, the other one won't be spontaneous, okay? And make sure that you give me that E naught value, tell me if it's spontaneous or not, and then show me the overall balanced equation. So on each one of those, on 33, A and B, 36, A and B, and those are the 3 bits of information that I need to clearly see. Spontaneous, non-spontaneous, E naught value, the equation. Okay. Now, let's talk about 47. So 47 boils down to the wording. It says, place the following in order of increasing strength as oxidizing agents. Okay? So if you look, you've got like CD2 plus, iodate 1 minus, potassium, water, AuCl4, and I2, right? So if you look at this, you want to rank these in order of increasing oxidizing agents. So you have to understand first, what do oxidizing agents want to do?
Reduce.
Meaning they want to do what?
Gain.
They want to gain electrons, right? So what you want listed first is which of these species is going to be least likely to take in an electron. Okay? That's the fundamental question that you want to ask, right? Which one of these is going to be least likely to take in an electron? So where are you going to look? Are you going to look towards the bottom of that reduction chart, or are you going to look towards the top? Bottom, okay? So you're trying to find the one that's least likely to take in an electron. So let me give you a hint. That should start with potassium ion, okay? So your first species that you're going to list on 47 is going to be potassium, okay? And then you're going to go up from there, and the last one is going to be IO3. So those are your bookends. What happens in between is up to you, okay? On 49, you should have 2 no's and 2 yeses. Okay? 2 no's, 2 yeses. You figure out where they go. On 50, you should have 1 yes and 2 no's. Again, you figure out where that is. Now, let's talk about 51. Okay? So, if you look on 51, and by the way, if you all really want to start to plan ahead, the test over all of this whole redox unit, is going to be like, obviously not this Friday, not that cruel, but it's going to be like that last Friday
After spring break?
The Friday after
Okay.
spring break. Okay? So, because we got like a lab that there's 2 more labs that we have to do, and one of them is a 2-day lab, which will start tomorrow, and then finish up on Friday. And then we have electrolysis, and we have a lab that goes with that, and then that's kind of the story. So if you really want to plan ahead, that's when the test is going to be. All right, so if you look on 51, it says which is the strongest oxidizing agent? Okay, so first off, you're only going to have one potential answer. So if you look on 51A, what are you trying to find? The one that's going to be most likely to do what? Meaning take in an electron, right? Okay, that's what you're trying to find. So let's look at the difference between Zn2 plus and zinc. Okay? Let's say I gave you that option. Just let's say I gave you this option. Which is going to be the better oxidizing agent? Zn2 plus or zinc? Zn2 plus, right? Because why won't zinc gain an electron?
Because it doesn't want to, it's already elemental.
Yeah, it doesn't need to, okay? It's a metal, right? If it gained an electron, and again, in your esteemed chemical careers, have you ever seen Zn1 minus?
No.
No. Okay, you know why? It doesn't do it, okay? Now, have you seen Cl1 minus?
Yeah.
Yeah. Though chlorine takes an electron because it becomes more stable, okay? Your metals aren't going to gain electrons and turn into anions, okay? Zn2 plus at least has the capacity to gain electrons and turn into zinc, okay? So Zn2 plus could at least have the possibility. Now, if I said, which one of those is going to be the best reducing agent?
You'd say Zn,
Then I'd say zinc. Why?
because it wants to go this way.
Yeah, zinc really, really wants to lose electrons because when it does, that puts it at the bottom of the energy well. Okay? So that's what you have to keep straight. Right? So, if you look on your chart, where on the answer for 51, where are you going to look? On the left side of that chart, on the reactant side, or on the right side?
Like,
You're going to look on the reactant side, right? Are you going to look towards the top, or are you going to look towards the bottom?
top.
Look towards the top. So that first one is, the first answer on 51A is Ag plus. Okay? Now, don't put Ag, because there's a huge difference between Ag plus and Ag. Silver itself is not going to gain an electron. Okay? It's not. Ag plus will. And that's what you have to keep track of. Are you talking about elemental silver, or are you talking about the Ag ion? Okay, huge difference between the two of them. Okay? So, when you get to B, you've got which is the strongest reducing agent. So what are you asking to find? The one that is most likely to get, and the one that's going to be most likely to lose electrons. Again, are you going to look on your reduction chart, or are you going to look on the reactant side, or are you going to look on the product side of your reduction chart?
Product.
You're going to look on the product side, top or bottom of the chart. Down towards the bottom, up towards the top. Up on the rooftop, clap, clap, clap. But, right, because you're going to find the one that's going to be most likely to get reversed, okay? On 51C, you should have two answers to 51C, okay? So if you look at what's happening on 51C, which species can be oxidized by the SO4 sulfate ion in an acid, right? So if you look on that chart, you can find SO4 2 minus the reduction of SO4. So you're going to try and find, and again, you can do the E naught value, you can try and find the ones that produce positive E naught values, or you can do the over-under game, okay? But basically, if this is a tug of war, what you're trying to find are which elements are willing to give up electrons to the sulfate, okay? That's what you're trying to find, right? Now, think about this. Let me give you a hint. One of these is going to be zinc, okay? So one of your answers on 51C is going to be zinc. Now, but here's the question. Is it zinc, or is it Zn2 plus?
Zinc.
Zinc,
Why not Zn2 plus?
because zinc 2 plus would not want to be oxidized because it's already at a higher energy state.
No, it's already at a lower energy
Or,
state.
yeah.
Okay? So the Zn2 plus is already at the bottom of the energy well, right? It's not going to go anywhere. Okay? It's not going to lose more electrons and become Zn3 plus. You know why you never see Zn3 plus? It's not stable. It's not going to happen. Okay? So this is what you want to think through. Which one of these is going to be most likely to lose electrons? Zinc or Zn2 plus? That's the thought process that you want to have. Okay? And then the same thing on 51D. You should have two answers to 51D. Should have two. Okay. Anything else?
No.
Now, notice on 51, it says, give reasons for your answers, okay? I just don't want the answer. Now, there's any number of ways you could answer. You could say, oh, you have a positive E naught value, or it has the smallest E naught value, or it has the largest negative E naught value, okay? Or the sum of these reactions produces a positive E naught, okay? So make sure that you haven't just said, oh, here are my answers, okay? You don't have to write a doctoral thesis, okay? But at least give some justification for that, okay? Anything else on that assignment? Going once, twice, so. Okay. Yeah, stop that for a second. All right, so today, here's kind of the second to the last big topic that we have to cover. And that's what's this concept of Gibbs Free Energy. So, no, I'm not going to ask you like when he was born or when he died, but it just kind of gives you some perspective as far as like the history of when this took place. So, Gibbs was actually described by, and this is impressive, he was described by Albert Einstein as one of the most brilliant mathematical minds that existed in science, okay? So for Albert Einstein to say that about you, that's okay. Yeah, it's like, I'll put that on my resume. Hey, Al, can you write me a letter of recommendation about it, buddy? Okay, I got you, okay? So, but he died well before Einstein actually started to do his work, because Einstein really did his work, in like around 1910, 1920, that type of thing. So Gibbs had already passed away, but his work lived on well past that. So again, this is just so you have some perspective when this happened. So actually, the irony of it is when you look at what Gibbs did, he actually died before there was any mention of electrons, protons, neutrons. We hadn't found any of the subatomic particles when he died, okay? So it isn't like, he lived in the 50s and 60s. Okay, this is well before this. So in terms of Gibbs Free Energy, so here's kind of an example. So if you look at like a voltaic cell like I showed you before, where you had, you had copper ions and you had a strip of copper, and you had zinc, and you had zinc ions, and we could put that salt bridge across there, and that current would go out and it would flow through the voltmeter, okay, we got the reading. So the idea of Gibbs Free Energy is that it's free in the sense that you don't have to do anything to produce it. So you could take those electrons that are moving, and you could like make a light up, okay, or something, okay? It's free. You don't have to do anything to make it happen. All you have to do is set up the cell. Once you set up the cell, then that's what's going to take place. So if you look at what Gibbs Free Energy talks about, so one of them is what we call work max. So for those of you that have had physics, what's the simplest way to calculate work? Force times the distance, right? So to do work, you have to exert a force over distance. So like if I take my can of Dr. Pepper and I lift it up, I do work because I exert a force through a distance. If I push it, I do work. I exert a force through a distance. So when you calculate this Gibbs Free Energy in terms of a cell, if you could harness that energy, that's how much work you could do, okay? To push something, to pull something, to charge a battery, whatever that is, okay? Now, so if you say, hey, if in the question it says, what's the maximum work that a reaction can perform, your maximum work is the same as your amount of Gibbs Free Energy, okay? So that means the same thing. So here's a good way to kind of visualize this, and for those of you that on my AP chemistry class, you all saw this yesterday. So this is a hand crank generator. And I've got it hooked up to like an LED light, okay? So if I want to make that LED light up, the energy isn't free because I've got to turn this handle. So when I turn this handle, I'm doing work, okay? I'm exerting a force over a distance. So when I do that, I can make that LED light up. Now, as soon as I stop, light goes back out. So I'm doing work because I'm exerting a force over a distance. But it isn't free because of the fact that I had to exert a force over a distance. If I just build a cell, okay, and I let the reaction take place, that flow of electrons does the work, and it could light up the LED light, okay? But in this situation, I'm going to do work, but the work isn't free because I'm the one that has to exert the force over the distance to make the light shine, okay? Got that? Now, in terms of your mathematics, the equation that you're going to use, and this is on your equation sheet, okay, don't memorize it, but it's negative n times F times E naught. So F is what's known as Faraday's constant. It's named after Michael Faraday. He actually wasn't trained as like a scientist. He was actually trained as like a bookbinder, but he started hanging out with all of the scientists, and this was in England in the 1800s. So there's any number of things that came out of Faraday. And he was just, they say it actually helped him that he wasn't like a trained scientist. He went in with an open mind. He did a lot of work with experiments involving electricity, okay? So one of the things they came up with is this concept of what's known as Faraday's constant, and that's what that big F stands for. So Faraday's constant is the amount of charge, and I'm not going to expect you to know how to calculate this. I'm just showing you where the number comes from, okay? So Faraday's constant is the total amount of charge on 1 mole of electrons, okay? So if you have 1 mole of electrons, 6.022 times 10 to the 23rd, each electron has a fundamental amount of charge called a coulomb, 1.6 times 10 to the negative 19th coulombs. So, and that's just like a fundamental part of it. Just like each electron has a certain amount of mass, each electron has a certain amount of charge. Now, the cool thing about it is that a proton has the exact amount of charge as an electron, but it has a positive charge, okay? So, where this number comes from is if you take 1.602 times 10 to the negative 19th coulombs per electron, and you multiply that by Avogadro's number, 6.022 times 10 to the 23rd electrons per mole, okay, because that's the number of particles per mole. So, your electrons cancel out and you get coulombs per mole. So that's the amount of charge it has per mole. Now, how you actually use Faraday's constant isn't coulombs per mole, and you'll see why we changed this up a little bit. How you actually, what you're going to use in this class is joules per volt mole. Now, the reason that this works is that volts is a measure of energy. It's how much energy you have given this electron. So if you substitute in joules per coulomb here for volts, which is what volts is a measure of, then what happens is that the joules, which is a measure of energy, okay, then what's going to happen is that the joules cancel out and you get coulombs per mole and you end up back where you started. So what you're going to functionally use in this class for Faraday's constant is joules per volt mole, okay? It's usually just coulombs per mole, but this is going to make the units work out better. It's the exact same number, it's just what units that you put on the end of it, but they're the exact same, okay? Now, what's going to be important is that that is per mole, okay? That's going to be, that mole is going to play out large later on. All right, now, when you calculate delta G naught, and when you see delta G naught, again, that naught just means what?
Standard condition.
It's under standard conditions, 25 degrees Celsius, 1 atmosphere of pressure, all this good stuff, okay? So, this is negative N. Now, this N is the number of electrons from the balanced, and I have to emphasize this, the word balanced, equation from the half reactions, okay? So this is gonna be like, when you equalize to do half reactions, so maybe like one is 5 and the other one is 2, and you multiply them together, you'd have like 10 electrons. So that N is going to be the number of electrons from the balanced two half reactions, okay? That's the number that you have to have. Then you have F, which is Faraday's constant, and then you have E naught, which is a measure of volts. So if you look at what happens to the units, you got negative N, which is the number of moles of electrons, okay? You're going to multiply that by Faraday's constant, which is 96,500 joules per volt mole. And then you've got E naught, which is in volts. So basically, the volts cancel out, moles cancel out, you're left with joules, voila, that's why it works, okay? That's why you can't have it in terms of coulombs per mole, because then you don't get the right units to work out at the end. Okay, so that's why Faraday's constant has the units that it has. So when you look at the potential values for delta G naught, one, delta G naught could end up being a negative number. So if delta G naught is a negative number, that means the reaction is spontaneous, and it's going to take place. If delta G equals 0, the system's at equilibrium. And if delta G is a positive number, that dog won't hunt. Okay? That's going to be a non-spontaneous reaction. Okay? It's not going to happen. So those are your three possibilities. Now, this is where you have to look at this reaction like holistically. All right? So if you look at delta G naught equaling negative, that was horrible, N, negative N, Faraday's constant, E naught. So this is where this thing goes hand in hand. Well, N is the number of electrons. That can never be a negative number because it's just the number of electrons. Okay? Faraday's constant, that's just 96,500. That number can never be negative. Okay? But then you get into E naught. Okay? Well, think this through. If E naught is a positive value, okay, so look at what you know so far. If E naught is a positive value, is the reaction spontaneous?
Yes.
Yes. Positive E naught values make spontaneous reactions. So this is the significance of this negative sign right there. Okay? Because that negative sign is going to say, wow, if all of these are positive numbers, that makes it negative. I get a negative delta G naught. Oh, here we go. We're off to the races. I'm going to get a negative delta G. Okay? So a positive E naught value would generate a negative delta G. Okay? Now, if E naught equals 0, okay, think this through. If E naught equals 0, are any electrons going to move? No, the system's in equilibrium, right? Okay? Battery is dead. Nothing's going to move. Well, if there's no potential for the electrons to move, guess what? You can't do any work because the electrons aren't going anywhere. Okay? There's nothing to be gained. You're at the bottom of the energy well. Now, if you have a negative E naught value, now what do you know about the reaction? It's non-spontaneous. Then you're going to have a negative times a negative. You're going to get a positive delta G. Guess what?
Non-spontaneous.
It's non-spontaneous. Okay? Okay.
So if delta G is positive, that would mean work max is positive, right?
Yes, but there just wouldn't be any work done. I mean, because there would be nothing to do. But yeah, you're right.
I just don't understand like why the negative sign is needed. If you like, why does delta G have to be negative if it's spontaneous?
Here's the reason why. There's a whole bunch of different ways to calculate delta G. That's one of them. This one we'll talk about when we get into thermodynamics. This is like the mother of all thermodynamic equations. Okay. So, and again, do not write this down. We're going to spend 2 days talking about just this equation.
Thank God.
So here's the other way that you can calculate
Oh my God,
delta
enthalpy and
G naught.
entropy.
So it's delta H, which is enthalpy, okay? Enthalpy is how much energy there is in a reaction, okay? It indicates the direction of the energy flow. Is it exothermic? It's like burning gasoline and energy is going to be given off. Or is it endothermic, where it's going to draw energy into the reaction? T is your temperature, okay? Has to be in Kelvin. Delta S is entropy. Entropy is a measure of the disorder in the system. So this is why this has to be consistent. So with this reaction, again, if you have a negative delta G from all of this, you get a spontaneous reaction. If this is a positive delta G, then the reaction's not going to happen. So this has to mesh with that NF E0. So that's why you have to have that negative sign in there. So then it becomes consistent with this idea from this equation. And this is actually the bigger idea about Gibbs free energy. So that's why you have to have the negative sign in. Okay, so here's how this would work. Let's say okay, so here's what would happen, and this is how this would physically take place. First off, you have, I already balanced the equation, so you don't have to worry about that, okay? So you've got 4Ag, so what would you, first off, what would you, if I said, hey, I want to set up this reaction as a demo, what's the first thing you'd have to get me?
Silver.
Yeah, you'd have to give me a piece of silver, okay? I'd have to have some elemental silver, okay? Then I'd have to have oxygen as a gas. So I'd have to have like some source of oxygen gas, maybe from a container, maybe like the decomposition of hydrogen peroxide. But I'd have to have something that's generating oxygen gas that I could bubble in. How can I get a bunch of hydronium ions? Yeah, add nitric acid, sulfuric acid, something like that. So basically, I drop in a piece of silver into an acidified solution, and I'd bubble some oxygen gas through it. Okay, or I could just let it sit out I could let it sit outside, because we got a bunch of oxygen in the air. I can also just let it sit outside, and the same thing would happen. Not as quickly, okay, as if I just bubbled the oxygen through it. Now, I'm going to end up with 4Ag plus, okay? So, what would you see happening to the silver?
It'd be dissolving.
It'd be dissolving, because it's turning from elemental silver into silver ions. So if you let this reaction run, you would see the silver dissolve, because it's turning from elemental silver into silver ions. So over a period of time, the silver would dissolve. Okay, so it's handy if you can kind of visualize what's taking place in that reaction. So, the first thing I've got to figure out is my E0 value. And I also have to figure out the number of electrons that are involved. Now, I can't figure that out based upon this. So let's think this through. Do you want to do the reduction part or the oxidation part first?
Oxidation.
Okay, we'll do the oxidation part. So on my oxidation, what's my oxidation reaction?
4Ag.
Yeah, it's just 4Ag turning into 4Ag, Ag plus 4 electrons, right? Okay, that's what I got. That's my oxidation part, right? There you go. Now, the reduction part, this is where you've got to use that bigger table that I gave you. So, on the reduction part, you need to look for the reduction of oxygen to produce water. Now, this oxidation here, what's the E naught value for the oxidation of silver?
For the oxidation of silver, negative 0.8,
Why negative?
because it went in the opposite direction.
Bingo. Okay? So my E naught value for the silver is going to be negative E naught. Okay? So that means this part of the reaction is as a negative E naught. Okay? It's the reverse of what you have, right? So on the reduction part, okay, and this is where you have to have like that bigger table. So your reduction part is going to be 4H plus O2
Plus 4 electrons.
electrons is going to yield 2H2O.
That's on our smaller table too.
It is?
Yeah.
Okay, so what's that reduction potential?
1.23.
1.23 volts. Okay? So basically, what you're doing is that you have an acidified solution and you're dumping oxygen into it and you're going to produce water. Okay? So, at this point, we know to calculate delta G naught, we're going to have negative N, Faraday's constant, times E naught. So, my N value is going to be what? 4. Don't look at that silver. This is why you have to have the overall balanced equation. Because the silver by itself is just going to involve one electron. This is why you have to have the overall balanced half reaction so that the number of electrons lost equals the number of electrons that are gained. Okay? So that's why you have to have that. So, you're going to have negative 4, and then you're going to have 96,500 joules per volt mole. And then, now what's my E naught value?
It's going to be positive.
Should be 0.43, I think. 1.2, yeah, 0.43 volts. So my volts are going to cancel out. I'm going to get joules per mole.
Shouldn't your moles cancel out then?
Because, now, I'm going to tell you now, this is where this concept of moles gets a little bit weird, okay? And it always creates a little bit of a problem. Because this is like 4 moles of electrons, but what this number is going to represent overall, in terms of what you're going to calculate, is joules per mole of a particular reaction, okay? So the bigger picture is that this is how much energy is going to produce per mole of a particular reaction. So a lot of times it varies from book to book. Sometimes they'll go ahead and put in joules per mole, and that's more actually correct. And you can sit there and go, well, this is like 4 moles of electrons, so why doesn't that cancel out? Because the overall picture is that you're looking at, this is how much energy that is being released per mole of the entire reaction. So moles get a little hinky when you do thermodynamics. So
that's
anyway.
joules per mole for right
Yeah,
now.
so just put down joules per mole when you can't go wrong. So this should be like negative 170. Now, on this deal, you can either put this in, because if you actually multiply this out, what do you get when you actually multiply it out?
Negative 1.66 e to the 5th. joules
Negative
per mole.
1.66
E to the 5th. Joules per mole.
e to the 5th.
Yep.
Now, that's in joules. Now, if you don't like writing exponents, there's 1,000 joules per 1 kilojoule. So if you don't like that, you can lop off 3 zeros, and then you could write that as like negative 167, that's 1, kilojoules per mole. I don't care how you roll, okay? Kilojoules, mole, kilojoules, joules, I don't care. It's up to you. Just make sure that I know which one it is, okay? Just don't write down a number and expect me that I know which one it is, okay? So if you want to leave it in joules, fantastic. That's great. But if you want to change it into something else, then you need to, if you want to put it in kilojoules, put it in kilojoules. So is the reaction spontaneous?
No.
Yes.
Yes. Oh, it's a negative number.
You have a negative delta G and you have a positive E naught. Okay? You have a positive E naught value. Now, if you reverse this reaction, nothing's going to happen. Okay? So if you start with Ag plus, if you dump silver ions into water, you're not going to generate oxygen and elemental silver, which would be cool. It's like, oh, you want to make some silver? Here, we'll just dump silver nitrate into a bottle or into some water, and wow, we're going to make silver. Okay? Which would be cool, but not going to happen. Okay, got it? Good, grand? All right, stop that for a second. Okay, number one, do not put the answers on this sheet, okay? Treat this as like a page out of the textbook, okay? I want this done on another sheet of paper. So, basically on 1, 2, 3, and 4, I'm going to say, hey, calculate delta G naught, or I'm going to say, calculate the maximum amount of work. It means the same thing, okay? So, some of those, I kind of give you the overall reaction. You have to figure out what's going to happen in terms of the redox. When you get to like 4A and 4B, I've given you the two half reactions. You just have to figure out which one's going to get flipped and which one's going to stay in that direction. And so you're going to have to look at your chart to figure that out. When you get to 5B, okay, 5B is a stoic problem. And I want to say, how many grams of chlorine gas would you need to produce 286 liters of chlorine dioxide under standard conditions? So if you remember back from your stoic, some of you might have ever seen this, but under standard temperature and pressure, 1 mole of any gas occupies 22.4 liters. So 22.4 liters is about the same volume as that jug of water that's up there, okay? So that's, I gave you that number, but that's where that comes from. Now, when you get to question number 6, 6 is very similar to question number 51 on the assignment that you had today. I want to say, which is the strongest oxidizing agent? Explain. Which is the strongest reducing agent? Will iron dissolve in a 1 molar solution of cesium 4+? Okay, so in other words, will iron lose electrons to Ce4+? Which of the following can be oxidized? Which of the following can be reduced by hydrogen gas? Okay, so I am done. You got about 20 minutes. You're on your own.